Hello there and welcome back to the Science Sleepy Minds. Above you the sky yawns wide, stitched with stars and bruised with the soft haze of ancient light. A comet brushes the edge of your vision like a slow-moving eyelash. Below, the world is a memory. Quiet, soft, irrelevant. You're here now, in the cool infinity of space where everything feels still but nothing actually is. Tonight, we're unraveling a simple, dangerous question: does space end? You probably won't survive this answer. Not because of some tragic cosmic radiation event, but because your brain might turn into a warm soup of paradoxes before we even hit Section 5. There are no seatbelts out here, just curiosity, old starlight, and the oddly comforting knowledge that nobody knows what's really going on. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're tuning in from, and what time it is in your little corner of the cosmos. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're lying on your back, maybe on the hood of a car, maybe on the roof of a two-flat apartment complex, maybe just on a blanket in some mosquito-filled park that definitely closes at dusk. You're looking up, and at some point, while watching a satellite blink by or pretending you can spot Ursa Major, you think it. Where does it all stop? That's not just a random stoner question. It's a question that physicists, philosophers, priests, and small children have all asked unprompted for literally thousands of years. It's baked into our brains. You see a thing, you want to know what's outside it. You hit a wall, you knock on it. You find a door, you open it. And when you can't find either, well, you invent the idea of infinity and pretend that helped. The ancient Babylonians believed the sky was a solid dome, called the firmament, over a flat earth. A ceiling that held back the cosmic waters. Very stylish. The Egyptians, not to be outdone, imagined a starry goddess named Nut arching over the world, her toes on one horizon, her fingers on the other, holding up the sky like a yogi in a plank. And we're not even getting into the Norse, where the earth is encircled by a massive sea serpent and the sky was literally made from a dead giant's skull. Yes, someone definitely got high on birch bark before writing that one down. But here's the thing. Every one of those early models included an end, a boundary, a point beyond which you could not go or should not. Even today, the idea of space ending still sneaks into our language. We talk about the edge of the universe as if it's a cliff you could bike to, or worse, a wall you could hit. It sounds poetic, but it's also misleading. The modern concept of the observable universe is often mistaken for the whole thing, but it's not. It's just the part we can see, roughly 93 billion light years across, centered on you. Not because you're special, you are, but not cosmically, but because that's how light works. That's how space works. Light takes time to travel. You can only see as far as light has had time to reach you since the Big Bang, about 13.8 billion years ago. And yes, things can be farther away than 13.8 billion light years. The expansion of space means that the edge of your observable bubble includes places that have moved away while their ancient light was still en route to your retinas. So even that number isn't a hard edge. It's more like a fading horizon. You move toward it, and it moves away from you, like trying to reach the end of a rainbow. Spoiler alert, there is no pot of gold. There might be some dark matter, though. It's like gold, but unobservable and kind of rude. Historians still argue whether the ancient Greeks fully understood the implications of an infinite universe. Some schools, like the atomists, flirted with the idea of boundless space. Others clung to perfect crystalline spheres, because what's more comforting than thinking planets run on clockwork? And then there was Aristotle, who insisted the cosmos must be finite because the heavens were too perfect to be infinite, that aged like milk. So what does space look like from your perch here, lying flat with your mouth slightly open and your thoughts slowly unraveling? It looks full. Of stars, of galaxies, of microwaves, and particles, and weird distortions in background radiation that make scientists write very long papers. But even if the visible parts are crowded, the structure of space is, well, more like a sponge, or foam, or a terrifyingly gigantic web. Galaxies form filaments that stretch across incomprehensible distances, separated by a void so empty, even a single atom would feel lonely. You float deeper into this spongy mess, and for a second it really does feel like it should end, right? Everything else ends. Beaches end, movie credits end, and even that really uncomfortable conversation you had with your boss. Eventually, it ended. But space? It doesn't seem to follow the rules. Here's the kicker. There might not even be a rulebook. One fringe theory, just a little bedtime snack for your anxiety, is that the universe isn't a thing in space. The universe is space. Asking what's outside the universe is like asking what's north of the North Pole. You can walk all the way up, plant your little flag, and then what? There's no northier direction to go. Of course, even this analogy breaks down. Because the Earth is round, but is space? Oh, we'll get there. But for now, just lie still. Listen to the hum of starlight and forgotten radio waves. Feel the gravity of curiosity pulling you forward. The stars above you are older than language, and yet they whisper the same questions every night. How far? How big? What happens when it ends? Maybe nothing ends. Maybe it wraps. Maybe it folds. Maybe space is like your inbox, ever-expanding, slightly cursed, and full of unread messages from earlier epochs. But one thing's certain, we're just getting started. You begin to move, not falling exactly, but gliding through that familiar, not quite there sensation that only exists in dreams and quantum thought experiments. The stars rearrange around you, constellations warping like spilled glitter in zero gravity. You're headed backward in time and deeper into the human urge to draw borders around the unknowable. Long before telescopes, equations, and the smug clarity of PowerPoint presentations, people still looked up and asked the big questions. But with none of the tools we have today, they had to get creative. And by creative, I mean wild. Welcome to the world of cosmic cheese wheels, skywalls, and dome theories. So earnest they kind of hurt your heart. The ancient Mesopotamians believed the sky was a solid dome, an actual ceiling, possibly made of polished stone or something metal and reflective, like celestial brass. This firmament wasn't poetic metaphor, it was structural. It held back the waters of chaos. Stars were literally tiny holes poked in the dome to let divine light leak through, which, honestly, is a pretty good aesthetic. Very Pinterest. The firmament idea shows up again in early Hebrew cosmology, and even sneaks into medieval Christian maps of the universe. You had the Earth, sitting politely in the middle, surrounded by concentric layers, air, stars, planets, and then, of course, heaven, floating up at the top like some immaculate VIP lounge. Everything had an edge, a place, a name, a purpose. You may be floating through the void now, with dark matter brushing past your hair like dry wind, but humans once imagined the cosmos as cozy, like a snow globe made for giants, with rules, borders, cosmic zoning laws. The Earth wasn't just in the universe, it was the universe. And yet, not everyone bought that model. Around the 4th century BCE, a Greek philosopher named Anaximander imagined a universe not as a dome, but as a boundless, undefined apeiron, a sort of limitless origin state. No walls, no edges, just infinite potential. It wasn't science as we'd recognize it today, but it was a definite departure from the cosmic ceiling club. Historians still argue whether Anaximander was picturing a truly infinite universe or just a conveniently vague one. The records are, let's say, poetically unhelpful. Either way, his version didn't have the comfort of edges. No firmament, no finish line, just something that went on and on. Fast forward a couple thousand years, and we arrive at a curious in-between phase. People are inventing telescopes, refining physics, and discovering celestial bodies that do not revolve around us, rude, but they still can't quit the idea of boundaries. Early cosmologists believed that beyond the stars there might be a crystal sphere. Beyond that, maybe a realm of fire. Beyond that, some kind of divine or mathematical edge wrapped in the love and judgment of a very patient God. Let's take a moment to appreciate Tycho Brahe, a 16th century Danish astronomer known as much for his stellar charts as for the metal nose he wore after a duel. Tycho proposed a hybrid model where the Earth stayed at the centre, but the other planets orbited the Sun, which in turn orbited us. Why? Because boundaries matter, and Earth being central made all the other circles make sense, or at least they felt like they made sense. We really do love putting ourselves in the middle of things, don't we? You drift now through the concept of the celestial sphere, a useful but imaginary model astronomers still use today. It imagines the stars as being fixed on a great spherical shell surrounding Earth. Not because they are, but because it helps us map things like star locations, constellations, and the precise time to make a wish on a shooting star that's actually just space debris. Here's the thing, even as tools improved and maps expanded, the concept of a limit was hard to shake. Even now we talk about the edge of the observable universe, as if it's some shimmering wall of pixels waiting to load. And you might wonder, if that's the edge of what we can see, is it also the edge of what exists? Nope, not even close. The observable universe is like standing in a fog. You can only see as far as the light has had time to reach you. But beyond that fog, things continue. Other galaxies, stars, maybe other yous, if the multiverse is having a particularly dramatic week. It's not an edge, it's a horizon, a boundary of perception, not of presence. There's a fringe but fascinating idea called the cosmic cheese theory. Okay, that's not its actual name, but some models describe the large-scale structure of the universe as being like Swiss cheese, matter clumped together in dense walls and filaments with enormous empty voids between them. So in a way, even the texture of space is filled with micro-boundaries. You're floating through a universe that's oddly holy and yet possibly infinite. And then there's the cosmic microwave background radiation, the afterglow of the Big Bang, still echoing through space. This faint hiss isn't just noise, it's a thermal map of the early universe. And it suggests something weird. Space has no outer shell, no boundary, just this gradual ancient warmth fading into what? More of itself. Of course, the urge to place edges on things isn't just about science, it's also psychological. Endings give us comfort. They imply structure, finality, purpose. A universe without edges? That's existential chaos. No top, no bottom, just a cruelly efficient void that doesn't care what you think about it. Kind of like your Wi-Fi router at 3 a.m. So maybe that's why we keep asking if space ends, not because we expect to find a brick wall out there, but because we're wired to think in containers, bodies, rooms, boxes, galaxies, all with some kind of lid. But you're not in a box now, you're in a swirl of stars, galaxies sliding by like marbles in molasses. There's no ceiling, no up, no down, only questions. What happens if you keep going in one direction forever? Do you come back around? Do you hit something? Do you stretch thin until you're light itself? Keep floating, we're not done yet. You drift outward, farther now, away from the warm cradle of human ideas and into the vast velvet ocean of modern cosmology. Galaxies slide past in every direction, glowing dots clumped together into webs and filaments, like spilled pearls on invisible strings. Everything is moving, but not through space. Space itself is stretching around you like taffy pulled in slow motion. Welcome to your bubble. Not a metaphorical one, although yes, your taste in sci-fi is pretty niche. This is the observable universe, your personal cosmic snow globe, roughly 93 billion light-years across and centered around, well, you. Not because you're the main character, but because this bubble expands outward based on your position in space and time. From every vantage point, the observable universe forms a sphere, radiating in all directions with the same dazzling indifference. It's like everyone gets their own cosmic dome, which feels inclusive, until you realize it also means you'll never see beyond it, no matter how good your telescope is or how many documentaries Morgan Freeman narrates. The phrase observable universe often gets mistaken for the whole universe, which is sort of like confusing the fish tank at a dentist's office with the Pacific Ocean. This bubble just marks the outermost reach of light that has had time to get to you since the Big Bang, around 13.8 billion years ago. But here's the catch. Because space has been expanding while the light was travelling Earth, the actual distance to the source of that ancient light is now about 46.5 billion light-years away. Yeah, time is weird, speed is worse. And when you mix them, you get a cocktail that breaks every intuition your brain tries to throw at it. Historians still argue whether ancient Indian and Buddhist cosmologies truly grasp the scale of infinity, but texts like the Surya Siddhanta describe vast cycles of creation and destruction, hinting at a cosmos far more expansive and less ego-driven than the geocentric models of Europe. Some of these traditions imagined universes stacked like lotus blossom, each one cycling through birth and death over unfathomable eons. So in a way, they beat us to the maybe this goes on forever punch. But back to your bubble. Inside it you can see about 2 trillion galaxies. That's right, trillion, with a T. And each of those galaxies contains billions or even trillions of stars, most of which probably host planets. If you feel small right now, good. That's the appropriate emotional response. It means your perspective is functioning. Of course, what lies outside your bubble is the real mystery. Because if space doesn't end, then this sphere you float in is just a teeny tiny patch of the full quilt, a single glowing cell in a cosmic organism we can't observe, touch, or even describe with confidence. But if space does end, then what is it ending into? A wall? A void? A big 404 universe not found screen? Cosmologists are split. The best current models describe the universe as either finite but unbounded, like the surface of a sphere, or infinite and just going on forever in every direction. Both options are unsatisfying in completely different ways. Let's unpack that. If the universe is finite but unbounded, it means it doesn't have an edge. But it still loops back on itself in a weird multi-dimensional way. Like Pac-Man, keep going right and eventually you come back in from the left. Only instead of 2D screen wrapping, it's 3D or maybe 4D, and your atoms never quite line up again. Wild. But if the universe is truly infinite, then your bubble is just a local flashlight beam in an endless cave. There's more out there. More galaxies, more matter, maybe even more copies of you doing this exact same sleepy science journey, but with better lighting and fewer existential crises. This leads us to a fringe but weirdly popular idea called cosmic redundancy. If the universe is infinite and matter arrangements are finite, which they probably are due to quantum rules, then somewhere out there, billions of light years away, there's an exact duplicate of you. Same socks, same thoughts, same embarrassing memory from middle school that you wish you could delete. It's comforting in a deeply unsettling kind of way, and if you kept travelling outward, bubble after bubble, region after region, would you ever hit a boundary? A sign that says end of universe, turn back now? Almost certainly not. There's no border patrol in space, no velvet ropes, just the slow, steady dimming of detectable information. You pass now through a simulated model of cosmic inflation, a graphic dream made real by math and microwave data. Galaxies are mere glitter specks. Voids yawn wider than the gaps between entire galaxy clusters, and at the edges of your reach the light fades into a whisper. That's the cosmic horizon. Not an edge, but a speed limit. A practical stop sign. Beyond it, the universe may go on. Probably does, but no information from that region will ever reach you. Not in your lifetime, not in any future version of humanity, not even if we become immortal tardigrade space wizards with tachyon-powered headsets, because space is not static. It's growing, expanding, not into something, but just more of itself. That's a key misunderstanding. When we say the universe is expanding, we don't mean it's growing into some surrounding void. It's not a balloon inflating in a room. The balloon is space. Every point in the universe is getting farther from every other point. Not because things are moving through space, but because the space between them is stretching, like dots on a balloon surface as it inflates. You're not flying away from other galaxies. They're standing still, but space is expanding between you. Quirky tidbit time. Some scientists once proposed that if the universe were infinite and unchanging, the night sky should be as bright as the sun in every direction. This is called Olbers's paradox, and thankfully it's not true, because the universe had a beginning, and light hasn't had time to fill the sky completely. Otherwise, bedtime would be way more complicated. So here you are, still floating, still inside your 93 billion light-year wide bubble, surrounded by galaxies, cradled in dark energy, and gently rocked by gravitational waves you'll never feel. Your cosmic snow globe is full of wonders, but it's just a blink of the bigger picture. Does space end? If it does, we've never seen it. If it doesn't, we may never understand it. Either way, you're in the middle of something breathtakingly incomplete. And isn't that kind of perfect? The stars begin to fade, not vanishing, just softening, like the dial on the universe's dimmer switch is being slowly turned. Galaxies drift farther apart. Points of light that were once close enough to map into constellations now feel separated by the stretch of eons. It's not your imagination. It's not metaphor. It's physics. And this is where things start getting weirded in the best possible way. You are approaching a horizon. Not the kind you can touch. Not the kind you can cross. A cosmic horizon built not from matter, but from time and motion itself. Specifically, from the expansion of space. Here's what you need to know. The farther something is from you in the universe, the faster it appears to be moving away. That's not because it's revving a galaxy-sized engine and peeling rubber across the cosmos. It's because the space between you and that object is expanding. The farther away something is, the more space there is between you, and the faster that space expands. This is Hubble's law. and it's one of the most important concepts in cosmology. Discovered in the 1920s by Edwin Hubble, with some serious help from Vesto Slipher, who deserves a cosmic shout-out. They noticed that distant galaxies always seemed to be moving away, and that the farther they were, the faster they receded. So now, imagine you're watching a distant galaxy drifting away. At first it's slow, like a balloon floating out of reach, then faster, then gone, not because it disappeared, but because it has redshifted out of the visible spectrum. Its light has been stretched by expansion until it becomes radiostatic, and then, eventually, undetectable. You didn't blink, it just crossed the line. That line is called the cosmic event horizon, and unlike the horizon on Earth, this one isn't about curvature or visibility, it's about speed. It marks the boundary beyond which light from objects will never reach us, not even if we wait forever. Not because they're too far, but because space is expanding faster than their light can travel. Historians still argue whether Albert Einstein fully accepted the implications of his own equations. His general theory of relativity allowed for an expanding universe, but he found the idea so uncomfortable that he added something called the cosmological constant to make the universe stay static. It wasn't until Hubble's observations that Einstein called that move the greatest blunder of his career, which is hilarious, because that blunder accidentally predicted dark energy, a concept we'll get to soon, and it may explain why space is still expanding faster and faster. You pass the cosmic event horizon now, not physically, but conceptually. The galaxies beyond this threshold are forever out of reach. They still exist, they still evolve, but we'll never see their future. It's like watching someone wave from the back of a train, only the train is moving faster than the speed of light and the track is growing as it moves. Space doesn't need an end when it can create distance-based exile this effectively. The weird part? Every observer, no matter where they are in the universe, sees the same thing. Their own event horizon, their own observable sphere. You're not special, everyone's in the middle of their own shrinking cosmic stage. It's equal parts humbling and horrifying. But let's not get too dramatic. Let's talk about the particle horizon. This one's a bit different. It marks the farthest distance from which light has had time to reach us since the Big Bang. Right now, that horizon sits about 46.5 billion light-years away. Yes, even though the universe is only 13.8 billion years old, that's because space has expanded while light was en route. Remember, you're not watching things as they are, but as they were, filtered through a universe that won't sit still. So between the particle horizon, what we can see, and the event horizon, what we'll ever see, lies the bittersweet core of observational cosmology. We're surrounded by stories we'll never finish, galaxies we'll never meet, and light that will never arrive. The universe is pulling away from itself. No explosions, no sound effects, just smooth, silent stretching. It's not going into anything. It's not expanding like a balloon in air. There is no outside of the universe because the universe is space. Expansion is not about motion through space, but of space itself increasing. Here's a fun and fringe tidbit for your stargazing dreams. Some theorists propose the idea of causal patches. These are like little bubbles of space-time that are causally connected. Everything inside can influence everything else, but beyond the boundary, no communication, ever. These patches form the basis for some multiverse models, where each patch is a self-contained universe, and space as we know it might be just a local phenomenon. In short, Boursier, your experience of space is limited by what light can do, and light is losing the race. You float now between receding galaxies, their light smeared across time. You reach out, and your hand passes through a beam of radiation that left its star 12 billion years ago. It flickers across your skin like a memory. That star might no longer exist. Its home galaxy may have merged, collapsed, or transformed, but its light tells the story anyway. And here's where it gets deeply poetic. Even if space doesn't end, your access to it does. As the expansion accelerates, more galaxies cross the event horizon every second. Eventually, only our local group, the Milky Way, and a few satellite galaxies will remain visible. Everything else will be gone, not destroyed, just elsewhere, unreachable, like pages torn from a book and scattered into the wind before you could read them. Quirky fact, in about 100 billion years, if some future civilization looks at the night sky, they won't see other galaxies, just darkness. They'll have no evidence of cosmic expansion, no clues, no Hubble, no redshift, nothing but their own stars, and a deeply misleading sense that they are alone in a tiny, still universe. That's the fate of cosmic isolation. Not because space ends, but because communication across it becomes impossible. So now ask yourself, what does it mean for space to end if its stories can still unfold forever beyond your reach? Is it a boundary or just a blur? You drift now at the edge of what can be known, not because there's a wall, but because the ink stops there. And yet the parchment goes on. You float with no sense of direction now, not because you're lost, but because direction itself is kind of a scam in deep space. There's no up, no down, no helpful "you are here" star map burned into the void. Just a soft background hiss and the shimmering spiderweb of the cosmic structure, humming quietly beneath your feet or above your head. Honestly, at this point, who's to say? And that's the perfect state of mind to start asking tonight's next question. What shape is all this? If space doesn't end, then maybe it wraps, or bends, or folds like a cosmic burrito filled with stars instead of beans. But before you panic, let's get one thing clear. No, the universe is not flat like a pancake, unless it actually is. And that, dear dreamer, is exactly the problem. The question of the universe's shape is one of those deliciously infuriating puzzles that keeps cosmologists up at night. Fortunately for you, you're already up, and possibly horizontal. Here's how this works. The shape of space depends on its geometry, which is affected by the amount of mass and energy it contains. And because Einstein had a flair for drama, his equations tell us that mass and energy curve space. So we have three major options. 1. Flat, Euclidean. If the universe has just the right amount of mass energy, critical density, then space is flat. Parallel lines stay parallel. Triangles behave themselves. And geometry teachers everywhere nod in approval. 2. Closed, positive curvature. If the universe has more mass energy than that, space curves like the surface of a sphere. Keep travelling in one direction and you eventually loop back to where you started. No wall, no edge, just a spatial boomerang. 3. Open, negative curvature. If there's less mass energy than critical, space curves like a saddle. No looping, just infinite expansion that fans outward forever. So which one is it? According to the best measurements from the Planck satellite and the cosmic microwave background radiation, remember that fuzzy baby photo of the universe? Space is, wait for it, flat, or so close to flat that we can't tell the difference. Historians still argue whether early 20th century astronomers like Willem de Sitter fully grasped the implications of a non-Euclidean cosmos. Some toyed with the idea of curved space long before it became fashionable, but it took Einstein and the wildly precise math of general relativity to drag the conversation into mainstream science. But here's the kicker. Even if space is flat, it can still be finite. Let me say that again for the sleepy people in the back. Flat infinite. Just like a video game map that loops when you walk too far in one direction, space could be both flat and closed, wrapped into a topology that tricks you into thinking it's infinite, when it's really just a fancy Mobius strip or 3D donut. Yes, that's an actual theory. The torus universe. Picture a cube where opposite sides are connected, so travelling through one face warps you back in through the other. You could go in a straight line forever, and eventually end up right behind yourself, cosmically photobombing your own past. You may now be wondering, have we tried to test this? Yes, kind of. Scientists have looked for repeating patterns in the cosmic microwave background, like echoes of ancient light that might loop through a closed universe. But so far, no definitive signs, just noise and suspicious symmetry, and the growing suspicion that the universe might be gaslighting us. Still, quirky cosmologists haven't given up. There are fringe models that imagine the universe with weird topologies, connected spaces, multi-dimensional tunnels, or even spatial structures that resemble certain knots. You might think this sounds like math cosplay. And, yeah, a little. But sometimes math cosplay becomes physics. Just ask string theory. Here's a fun thought experiment. Imagine you're flying a spaceship in a perfectly straight line. No gravity wells, no obstacles, just endless space. If you're in a closed universe, you would eventually return to where you started, though depending on the scale, it could take longer than the age of the universe. If it's open or infinite, you just keep going forever, like trying to finish the internet. And you might ask, How would we know if we returned to the same spot? Well, the universe doesn't come with road signs, but if we spotted the same galaxy in two different directions, looking slightly younger in one view and older in another, that would be a clue, a real testable loop in space. So far, no such luck, but we're still looking, slowly, patiently in between coffee breaks and existential spirals. Here's something else to bake into your mental lasagna. If the universe has a shape, then it also has a global geometry that affects everything from how galaxies cluster to how gravity behaves across the cosmos. It might even determine whether the universe has an end or just keeps repeating itself in wild topological ways. You glide now across imaginary surfaces. One moment you're skimming a sphere, the next you're tracing the lines of a saddle-shaped universe. And then flat, featureless, a cosmic carpet unrolling forever. Every geometry is beautiful, every possibility is slightly terrifying. There's even a fringe idea that combines multiple shapes into a single multi-connected universe, where space folds in chaotic, unpredictable ways. Think funhouse mirrors meets quantum spaghetti. Do not attempt to fold laundry in such a universe. Your socks will never match. Let's rewind a bit to our Paleolithic ancestors. They had no telescopes, no math, no cosmological models, but they still looked up and felt the stars pressing down. They still imagined the sky as a bowl, a tent, a barrier. Because boundaries are comforting, shapes are familiar, the unknowable becomes less terrifying when you can pretend it's round. And that instinct remains. Even now we design simulations, run models, launch satellites, all to map the shape of something we can't leave. You're like an ant trying to figure out the shape of its hill by licking grains of sand. Respectable, noble, doomed. So does the universe have a shape? Yes, probably. Can we know it? Sort of, with a lot of caveats, and some increasingly expensive telescopes. And does shape tell us if space ends? That's where things get wobbly, because a sphere has no edge, but it is finite. A saddle can go on forever. A flat plane might be either. Shape doesn't equal end, it just sets the rules for how space behaves. So maybe what we're really asking isn't does space end? Maybe it's, can we ever run out of space? You stretch your limbs now like the universe itself, calm, indifferent, vast. You're in a place where flatness might loop, where infinity might curve, and where ends might just be new beginnings disguised as geometry. So go ahead, keep floating. We've only just started sketching the edges of this invisible shape. You're still floating, but something's changed. There's a strange, prickly feeling behind your eyes, like your brain just hit a loading screen it wasn't ready for. That's because tonight, you're checking into the weirdest hotel in all of theoretical physics. No luggage needed, no reservation, just an open mind and a strong tolerance for infinity. Welcome to Hilbert's Hotel, the mathematical thought experiment that will completely ruin your ability to trust space, time, or occupancy limits. Picture this: a hotel with an infinite number of rooms, countable, orderly, all numbered, room 1, room 2, room 3, and so on. And every single room is full. Now imagine someone new shows up, a surprise guest. The kind of person who probably didn't read the cancellation policy. Can you give them a room? Weirdly, yes. You just move the guest in room 1 to room 2, room 2 to room 3, and so on. Every guest shifts over by 1. Now room 1 is free. You made space. Even though it was already full, you can do this for any finite number of new guests, or even a countably infinite number of new guests. Just shift everyone to double their room number. Room 1 goes to 2, room 2 goes to 4, etc. And all the odd-numbered rooms open up for your new arrivals. It breaks your brain a little, doesn't it? Because this isn't a problem with hotels. It's a problem with infinity. In a finite world, you can't fill something completely and still add more to it. But in an infinite system, the rules just don't work the same. They stretch, they bend, they allow for things that feel deeply illegal in every other part of life. This is where your cosmic brain starts to itch. Because if space is infinite, and the universe contains an infinite amount of stuff, then Hilbert's Hotel isn't just a metaphor. It might be a map, an actual functioning illustration of how the universe behaves. Historians still argue whether David Hilbert, the German mathematician who first proposed the hotel scenario, was seriously advocating for this kind of madness, or just trying to make a point about the absurdity of treating infinity like a real manageable number. Either way, the idea stuck. It's now a staple of set theory, cosmology, and late-night philosophical arguments that end with someone muttering nothing is real into a lukewarm cup of tea. But let's get back to space. If the universe is infinite, then the number of galaxies is infinite. The number of stars? Infinite. The number of ways atoms can be arranged into sentient snacks or philosophical jellyfish? Infinite. This is where the paradox of duplication comes in. Because if there are only a finite number of particle configurations possible in any region of space, and space is infinite, then eventually those configurations will repeat. Somewhere out there, there's a galaxy that looks just like the Milky Way, with a planet just like Earth, with a person just like you, listening to this same story, wondering why Hilbert's hotel has room service but no exit. It's not just theoretical fluff. Some multiverse models treat this kind of duplication as a near certainty, assuming inflation created vast regions of space that are essentially carbon copies of one another, endlessly repeating across infinite distances. But here's where the hotel gets even weirder. What if space isn't infinite in size, but infinite in divisibility? Quantum theory suggests that space might be quantized, made up of tiny indivisible units like pixels on a screen. If that's true, then space has a resolution, a lowest possible unit, and if that's the case, then even an infinite universe might just be really, really big, but still finite in how much it can hold. Kind of like trying to store an ocean in a really stretchy balloon. There's a limit. It just depends on how much stretch you allow, but most cosmological models, they don't like limits. The standard model of cosmology, called lambda CDM, if you want to impress someone at a physics-themed dinner party, treats the universe as effectively infinite. No edge, no border, no outside, just more of the same in every direction forever. And if that's true, then Hilbert's hotel becomes more than just a philosophical mind game. It becomes a pretty good approximation of how the cosmos behaves. Full, yet still making room. Busy, but never truly done. Here's a quirky side note that's real, and a little unsettling. If the universe is infinite and filled with matter, then there's a probability, however small, that random quantum fluctuations could produce a fully formed conscious brain floating alone in space, just thinking. These hypothetical entities are called Boltzmann brains, and yes, they're as disturbing as they sound. Even worse. Statistically, if such brains are possible in an infinite universe, they might outnumber actual conscious beings like us. So maybe you're not a person in a hotel in space, you're just a disembodied thought, hallucinating this entire narrative. Fun, to be fair. Most physicists consider this possibility horrifying and try very hard to explain it away with math and rationality. But it's out there, floating, like you. So what does this all mean for the question, does space end? If space is infinite, it never ends, but it can still surprise you. It can be infinite and still contain edges of experience, regions we can never reach, people we'll never meet, galaxies whose light will never touch our eyes. It can be infinite and still feel empty, or lonely, or strangely be familiar. Infinity doesn't mean everything happens. It just means everything that can happen does somewhere. And if Hilbert's hotel is right, then there is always room for one more possibility, one more galaxy, one more version of you floating like this, wondering if there's a cosmic checkout time. So here you are lying in room 4235, 781, 269 of the infinite cosmic hotel. You stare at the ceiling, which is also a galaxy. Your sheets are made of dark matter. Your dreams are stitched together from repeating quantum patterns. And outside your window, nothing ends. You blink, or maybe you don't, because time's starting to feel more like a flavor than a sequence. Everything around you has that dreamlike jelly consistency of early universe soup, where space, time, and logic are still negotiating the share contracts. You're falling backward now, way backward. Past the cosmic web, past the galaxies, past the first stars igniting like timid lighters in a storm. You're headed for the moment when space itself burst into being. You're diving straight into inflation, that awkward, overachieving phase at the very beginning of everything. And let me tell you, it's not subtle. Here's what you need to picture. For the first tiny fraction of a second after the Big Bang, the universe didn't just expand, it exploded outward in a staggering, almost comically aggressive burst of growth, and the numbers are ridiculous. In less than a trillionth of a second, space expanded by a factor of at least 1060. That's a 1 with 60 zeros. The cosmic equivalent of someone blowing up a balloon to the size of a galaxy before you can say, "Do you have a pump?" This brief but critical period is called cosmic inflation, and it may be the best explanation we have for why the universe looks so smooth, so uniform, and yet so massive and possibly infinite. The idea was first proposed in the 1980s by physicist Alan Guth, who was just trying to solve a few pesky problems in cosmology. Like, why is the universe so flat? Why does it look the same in every direction? And why don't we see weird, leftover stuff from before the Big Bang? Inflation answers all of that. By stretching the early universe faster than the speed of light, which, yes, is legal when you're not moving through space but expanding space itself, inflation smoothed out any wrinkles, any bumps, any early weirdness. It turned the frothing quantum mess into a pristine, seemingly infinite arena. It's like ironing your cosmic bedsheets at warp speed. Historians still argue whether the concept of inflation should be considered part of the Big Bang model itself, or a bolt-on theory that helps fix its early inconsistencies. Either way, it's become foundational. Most cosmologists now believe inflation happened, even if the exact mechanism, timing and exit strategy are still being hotly debated in whispered arguments over chalkboards and cold coffee. So what does this have to do with whether space ends? Well, if inflation happened once, it could happen again, and again, and again. This brings us to a deeply unnerving possibility: eternal inflation. In this model, inflation never completely stops, it just slows down locally. Pockets of the universe, like our own, finish inflating and form bubble universes, where stars, galaxies, and sleepy YouTube listeners can evolve in peace. But outside these bubbles, inflation rages on, endlessly creating more bubbles, more regions of space, more everything. Think of it like cosmic boiling. Each bubble is a universe. Some grow, some pop, some never form at all, and the boiling never stops. Now imagine an infinite pot. In this view, the universe doesn't just fail to end, it can't end. It's self-perpetuating. Each new bubble is a new universe, governed by its own laws of physics, its own constants, its own rules. Maybe in some, gravity is stronger. Maybe in others, atoms don't hold together. Maybe there's one where the laws of thermodynamics rhyme in iambic pentameter. You, of course, are in a bubble where the conditions happen to be just right for stars to form, planets to orbit, and cats to become internet celebrities. If eternal inflation is true, then space is like an endlessly branching fractal, each part sprouting new parts forever. There's no master map, no edge, just local neighbourhoods in an ever-growing, ever-splitting foam. Quirky side note, this cosmic foam idea actually shows up in quantum gravity research, where space-time might be made of discrete, fluctuating unitats that behave more like a foamy sea than a smooth fabric. So when we say bubble universe, it might be more than a metaphor. It might be how space actually works at the deepest level. You drift now between two inflating regions. One is calm, your own, rich with galaxies and background radiation. The other is still expanding wildly, violently beyond light speed. You can never reach it. No one can. Because as soon as one bubble forms, inflation pulls the rest apart too fast for them to connect. It's not just separation, it's causal disconnection, a permanent social distancing of entire realities. It also means this: space has no central origin, no special vantage point, no birthplace of the universe. Because the moment inflation began, it spread everything apart too fast for any such location to matter. And so the question, does space end, starts to sound a little silly. Like asking whether the surface of the ocean ends because you can't see land. Even if it did, you'd never reach it. The boat's expanding, the sea's foaming, and every attempt to point that way is just guesswork dressed in equations. Of course, not everyone agrees on eternal inflation. Some physicists argue it's untestable, that it predicts so many outcomes it becomes meaningless. If anything can happen in some universe, then what's the point of prediction? Others say that's the beauty of it. A framework big enough to hold everything, even paradoxes. Which brings us to your current position. Drifting in a space that might be infinite, might be finite but unbounded, or might be one tiny soap bubble in a sea of eternal expansion. You place your hand on the edge of your own universe, not a wall, but a gradient. A region beyond which your laws of physics don't apply. There's no barrier, no siren song, just a soft hum of difference, like a neighbour playing jazz through the walls of reality. And then, for just a moment, you feel it, the curve, not a shape exactly, not a direction, just the sense that this bubble you're in, this cosy, law-abiding universe, has siblings, and they're drifting too, quietly, forever. Does space end? Not if inflation has anything to say about it, not if the bubbles keep forming, not if your bedtime thoughts are bubbling right along with them. The air, or rather the concept of air, feels thinner now. Not because you're running out of oxygen, you're safe, remember, this is Bedtime Science Eve, not bedtime panic, but because the rules are starting to peel at the edges, like you're inside a video game and just walked into a glitchy corner where the textures haven't fully loaded. You're not just floating in our universe anymore. You're peeking between the seams of something larger. This is the part where space gets recursive, where the answer to does space end might not be no, or even yes, but not here, because it restarts elsewhere. Welcome to the multiverse, and friend. Population, literally everything. Let's get this out of the way quickly. When people say multiverse, they're often talking about different things, depending on how much math they've survived. In physics, there are multiple multiverse theories, and these range from plausible but unprovable to who let this through peer review. You've got bubble universes, quantum branches, brain collisions, and simulated layers stacked like pancakes made of math. Tonight, we're focusing on the version born from eternal inflation, which you floated through just a moment ago. Remember how new universes form like bubbles in an ever-expanding cosmic foam? Well, in this model, each bubble has its own version of space, its own physical laws, its own beginning, its own possible end. So maybe space does end in this bubble, but it just begins again next door, kind of like a cosmic strip mall, but every shop is its own reality. You push gently against the outer curve of our universe, not a wall, just a suggestion, and somewhere beyond it another bubble swells into being, one where gravity is stronger, stars don't form, atoms never coalesce, maybe even one where time runs backward and everyone communicates via interpretive dance. Historians still argue whether ancient philosophies hinted at multiversal thinking. Some interpretations of Hindu cosmology describe layered realities and cycles of universes being born and destroyed eternally. Similarly, certain Buddhist schools speak of countless world systems scattered across space and time, each with its own laws and timeline. But even then, nobody had the nerve to diagram it in PowerPoint, which is why modern physicists are still squinting at this idea like it's a magic eye poster they can't quite decode. Here's the fun twist. These other universes may not just exist out there. They may also be splitting off from you constantly. This brings us to the many worlds interpretation of quantum mechanics. In this view, every time a quantum decision happens, say whether Schrödinger's cat lives or dies, the universe splits. One version sees the cat live, the other sees it die. Both exist, both are real, but they can no longer interact. Every choice, every moment, every particle is spawning new branches of reality. You're not floating through one universe, you're drifting through a garden of infinite forks, a multiverse of maybes and what-ifs. Somewhere out there is a version of you who never heard of this channel. Poor soul. If that's true, then space doesn't end because it's not one space, it's every space. A forever branching tree of alternate timelines, quantum possibilities, and all the realities no one will ever visit, but which still exist, alone, complete. And just for spice, let's throw in brain cosmology, a string theory-inspired model where our universe is a three-dimensional brain floating in a higher dimensional space. Think of it like a cosmic slice of bread, and next to it, other brains, other slices, some close, some impossibly far, sometimes they even collide. One of those collisions, theorists say, might have caused the Big Bang. So now you're not just floating through our universe. You're drifting in a higher dimensional space where universes themselves are objects, passing sand like ships in a dark ocean. Some touch, most don't, but they are all real, and they might be endless, even if any single one of them ends. Here's your quirky tidbit of the night. One fringe idea in this brain model is that gravity might leak between brains, meaning the reason gravity is so weak compared to other forces, like electromagnetism or the strong nuclear force, is because it's diluted across multiple universes. Yes, that's right. Your inability to lift heavy furniture might be the fault of some other dimension's black hole sucking a bit too hard. Now, let's pause for a second. You might be asking, if other universes exist, why can't we see them? Good question, thoughtful sleeper. The answer is, we probably never can. The other bubbles from eternal inflation are separated from us by expanding space that's faster than light. The quantum branches of many worlds exist on entirely disconnected trajectories, And brains? Well, we don't even have the right kind of eyes or strings of energy to detect them. From your perspective, these other universes are like books in a sealed library. You can't open them, you can't borrow a cup of sugar, you can't even knock, but they're still there, probably, maybe, possibly forever. There's one more multiverse theory that's less physics, more existential drama, the mathematical universe hypothesis. This idea says that every mathematically possible universe actually exists. If it can be described with math, any math, then it's real somewhere. That includes universes made entirely of cubes, or pure logic, or code. Yes, that includes the simulation theory. We'll get to that soon. But in the mathematical multiverse, space becomes a relative term. It doesn't end, it just shifts formats. So how does this help answer our big sleepy question? If space ends in one universe, it begins in another. If it folds here, it stretches there. If it vanishes, it may reappear elsewhere with different stars or none at all. Maybe, does space end, is the wrong kind of question. Maybe the better question is, which space are you talking about? Because in the multiverse, all answers are true somewhere. You feel it now, the bubbling, fizzing presence of other spaces. Not visible, not touchable, but like a breath on your neck. Like the flicker of a dream that doesn't belong to you. You turn, but of course there's no one there. Just more bubbles, and maybe, just maybe, one of them is looking back. You float through the dark, and everything around you begins to loop. Not in the metaphorical sense, this isn't déjà vu or some poetic reuse of cosmic themes. No, this is literal. You're now in a universe where straight lines don't go straight. They circle back, and if you keep moving far enough in one direction, you just might smack yourself in the back of the head with your own past. Welcome to the world of topologically strange universes, where space may be finite, but still has no edges, where the cosmos might loop like a video game map, or a Pac-Man maze, or a hyperdimensional donut. Let's slow it down and picture it. You're on a spaceship hurtling forward at full speed, dead ahead. You set your course, mark your trajectory and go. No turning, no detours, just forward, forever. But after a very, very long time, say 300 billion light years or so, you arrive back where you started. Except you didn't turn, and the ship's GPS swears you went in a straight line. That's the paradox of a multiply-connected universe, a space that wraps back on itself like the surface of a sphere or a torus, or something even weirder. It's not infinite, but it has no boundaries. You can travel forever without ever hitting a wall because the path folds itself around. Kinda like living on a giant cosmic treadmill. Every step forward just rotates you around to the back again. Historians still argue whether the mathematician Bernhard Riemann fully understood the cosmic implications of his work on non-Euclidean geometry in the 19th century. He was the first to suggest that space might be curved subtly, quietly, in ways that Euclid never saw coming. Riemannian geometry laid the groundwork for Einstein's general relativity, and with it, the idea that space can wrap. It was a quiet idea, tucked inside chalkboard equations, but it changed everything. Here's where things get really spicy. The shape of space, its topology, can influence what we see in the sky. If the universe is looped or finite in a clever way, then light from distant galaxies might travel around the cosmos and reach us from multiple directions. In other words, you could be seeing the same galaxy from two different angles, millions of light years apart, like seeing the back of your head in a mirror from space. Astronomers have actually looked for these kinds of repeats in the cosmic microwave background, hoping to spot patterns or matched circles that would hint at a wrapped-up universe. So far, nothing conclusive. Just a lot of tantalizing symmetries and a growing suspicion that the universe might be better at hiding its shape than we are at detecting it. But the idea hasn't gone away. One of the simplest models of a looping universe is the three torus, like a donut but in 3 dimensions. Imagine taking a cube and connecting its opposite faces, top to bottom, left to right, front to back. Travel out through one side and you re-enter from the opposite. Like being inside a digital screensaver programmed by an existentialist. You could even have small universes this way, a universe just a few billion light years wide that feels infinite because it loops. You would never know, unless you caught the same object from multiple angles, or your own light echoing back from an earlier point in your journey. Quirky side note, a few researchers once proposed that the universe might actually be shaped like a dodecahedron, a 12-sided shape with pentagonal faces. Why? because the cosmic microwave background showed faint signs of suppressed large-scale fluctuations, something a finite looping universe might produce. Did it hold up under scrutiny? Not really. But it did get people excited about the idea that space could be less like an ocean and more like a cleverly folded origami swan. But let's step back. What does a looping universe feel like? You're drifting now, a straight line, forever. But slowly the stars begin to repeat. Not in an obvious way, not like wallpaper, but subtly. Familiar shapes, familiar constellations, familiar gravitational lensing signatures that only a very bored physicist would recognize. And then you see yourself from the side, then the back, then a future version of you that hasn't caught up yet. Time and space twisted together like a Mobius band, no walls, no edge, just topological gymnastics. This kind of universe challenges our instincts. We're used to the idea that infinity equals really big and finite equals has an edge. But in topology, that's not true. You can have a finite space with no boundary, like the surface of a globe, or a video game level that wraps around forever, or an endless hallway that leads right back to where you started. You might wonder, why does this matter? Who cares if space loops? Well, it might help explain certain mysteries, like the uniformity of the early universe, or why cosmic structures seem to align in weird, unexpected ways. Yes, there's a real thing called the axis of evil in cosmology. No, it's not a Marvel plotline, just a strange alignment in the cosmic microwave background that refuses to go away. And beyond the math, there's something almost romantic about it. A universe where your journey is never wasted, where every path folds back quietly into your own shadow, where the answer to "does space end?" is a gentle no. Just keep walking and eventually you'll come home. Maybe that's why we like the idea of a looping universe. It gives us closure without borders, a finite space with infinite promise. A cosmic road trip with no dead ends, just scenic routes that all wind back to familiar stars. Of course, we might still be wrong. The universe might be infinite and unwrapped, or it might be closed in a way that's so large it doesn't matter for practical purposes. Even a looped universe can feel endless if it's big enough. Like trying to find the seam in an invisibly giant sock. But if you ever do see yourself waving back through a telescope, don't panic, just smile. You made it around the loop. And now, you keep going, because maybe the real edge of space isn't out there at all. Maybe it's the point where your path folds quietly back on itself. No barriers, no warnings, just the soft hush of repetition. You've been drifting for a while now, through expanding bubbles, infinite hotel corridors, topological donuts, and recursive timelines that'll fold in on themselves like cosmic origami. But you've yet to hit a wall, not even a speed bump, no here be dragon sign, and no flashing border control. So now, maybe you're thinking, wait a second, if space doesn't end, does it at least have a border? Something, anything to mark the edge? Good question, thoughtful sleeper. The short answer is probably not. The long answer is yes, but only if you rethink what a border even means. Tonight we hover at the edge, not of the universe itself, but of our understanding of what an edge could possibly be in a universe that might have no outside to edge into. Because borders are usually about separation, between land and sea, between countries, between your food touching on the plate. But space plays by its own rules. Let's start with the obvious. What would a literal end of space even look like? Imagine travelling in one direction forever and suddenly stopping, like hitting a cosmic brick wall. What's behind it? Nothing. More space. A developer's debug room full of unfinished galaxies. The problem is, the moment you suggest a wall, you imply there's something on the other side of it. That space exists within something larger. But according to everything we know, and quite a few things we suspect, space isn't a thing floating in a bigger thing. It is the thing. It's not like a balloon inside a room. It's the balloon and the room. This is why most mainstream cosmological models say, there is no boundary. There's just more space, or no space, but never a wall. Historically, people weren't always so boundary averse. Ancient thinkers often imagined the cosmos as having a hard limit. Aristotle, bless his well-moisturized forehead, insisted the universe was a series of nested spheres, finite and ordered. Beyond the final sphere, the prime mover. That's philosopher speak for don't ask. Centuries later, Dante's Divine Comedy imagined heaven and hell as layered cosmic systems with fixed edges, carefully divided into zones like a celestial parking garage. It was all very well labelled, very organised, and deeply soothing to the medieval mind. But after Einstein, Newton's tidy little stage, the one where space was a passive backdrop, got completely obliterated. Suddenly, space was active, dynamic, stretchy, capable of warping and bending like taffy in a microwave, and in general relativity, you don't need an outside. The geometry of space determines itself. The universe can be finite without a boundary, or infinite without a centre. Quirky side note, there are shapes in math where this exact thing happens. Finite objects with no edges. The classic example is the Mobius strip. It has one surface, one edge, and if you trace your finger along it, you'll come right back to where you started, without ever crossing a border. Now imagine that concept in 3D or 11D, or 10 to 500D if you're feeling particularly string theoretical tonight. But let's go deeper. Even if space has no physical boundary, could it still have a conceptual one? Yes. That would be the observable horizon, which you've already crossed and recrossed on your sleepy voyage. This isn't a hard wall. It's more like the edge of a flashlight beam. Beyond it, the darkness isn't empty, just unlit. You can't see past it, not because there's nothing there, but because light from those regions hasn't had time to reach you yet. So technically, it feels like a border, but it's one made of time, not space. And then there's a wilder idea. What if space is like a boundary condition on something even more fundamental? In some quantum gravity models, like loop quantum cosmology, the universe might have emerged from a prior state, not through a wall, but from a bounce. Before the Big Bang, there was a prior contraction, like the universe breathing in before it breathed out. In this case, Dud's space didn't begin at a point. It flipped direction, and the boundary was just a change in behaviour, not a cliff. Even string theory gets in on the edge-faking game. Some versions describe our universe as a brain, floating in higher dimensional space, possibly bumping into other brainies from time to time. Do those higher dimensions have edges? Maybe. But if they do, they're not borders in any way we can currently detect or interact with. Here's where it gets even more deliciously abstract. There's a model called De Sitter space, which describes an ever-expanding universe dominated by dark energy. In it, every observer has a cosmic event horizon beyond which they can never receive information. Not because something's in the way, just because the expansion of space is pulling things apart fast, light can catch up. In this view, the universe is a kind of causal island. Each observer is surrounded by a personal border that grows more isolated over time. Not because space ends, but because contact does. So imagine you're standing on a cosmic shore staring into the ocean. That water stretches on forever, or maybe it curves around, but either way, there's no boat coming. Ever. The ships have sailed and the lighthouse light will never reach your window again. It's lonely, but kind of poetic, and it brings us to one final idea. What if the edge of space isn't out there at all? What if it's something that happens inward? As you travel farther, things become less observable, less knowable. Galaxies disappear over the horizon, the map thins out, but it's not because you found the border, it's because you found your limit, not of space, of you. You, the observer, are the one with edges, with perception limits, with redshift boundaries and lifespans and light cones. Maybe the universe isn't hiding its edge, maybe it doesn't have one. Maybe you're just slowly hitting the edges of what you can ever interact with, not because space ends, because you do. Now, no need to spiral. That's what Section 20 is for. You continue floating. No walls rise to stop you. No signs flash beyond this point nothingness. Just the slow dimming of familiar things replaced by deeper silence. So does space have a boundary? Not a real one, not a hard one, but you carry your own, like a flashlight beam, like a clock, like a soft edge drawn in chalk, always smudging as you move. And the universe? It never says stop. The darkness deepens now, but not in a frightening way. It's more like a gentle, velvet kind of dark. A hush, like the universe just put a finger to its lips and said, shh, listen. You do. And there it is, the faintest whisper, a nearly perfect hum, everywhere, always. is the cosmic microwave background, or CMB if you're on casual terms. The oldest light in the universe, the leftover glow from the Big Bang still stretching across space like the last embers of a fire that burned 13.8 billion years ago. It's not bright, it's not even visible to human eyes, but it's there, in every direction, a cold, almost boring presence that's somehow more important than any star you've ever seen. You're floating through it now, like passing through the breath of time itself. And here's where it gets real. If you're looking for clues about whether space ends, or what might lie beyond what we can see, this humble background hiss is one of your best bets. Let's rewind gently. After the Big Bang, the universe was hot. Not metaphorically, like this universe is, but literally a searing, plasma-filled furnace of particles and photons trapped in an endless high-energy soup. Light couldn't travel, the whole thing was opaque. Imagine trying to see across a room full of glowing lava lamps that keep exploding. But at about 380,000 years in, something miraculous happened. The universe cooled down just enough for atoms to form, electrons paired with nuclei. The soup became transparent, and light, finally, got to stretch its legs. That first light is still travelling today, but because space has expanded so much since then, it's been stretched too, redshifted from blinding white-hot energy into long, lazy microwave wavelengths. That's the CMB, the universe's baby photo, softly buzzing away in every corner of space. Fun, quirky fact. The CMB was accidentally discovered in 1965 by two engineers, Arno Penzias and Robert Wilson, who were just trying to eliminate annoying background noise from their antenna. They even cleaned bird poop out of the dish, thinking it might be the culprit. But the hiss persisted. Turns out they were listening to the literal birth of the universe. Historians still argue whether this was the most serendipitous discovery in astrophysics, or whether every experiment should now include a mandatory pigeon inspection protocol. But back to your float. The CMB isn't perfectly smooth. It has tiny fluctuations, cold and hot spots only millionths of a degree apart. These aren't random, they're the fingerprints of early quantum fluctuations, stretched across the sky by cosmic inflation. They're the seeds from which galaxies grew, and in their pattern we see the shape of space, the amount of matter, the rhythm of expansion. We also see something else, hints that maybe, just maybe, there's something beyond the observable, maybe even something brushing up against our universe from the outside. Some researchers have speculated that certain anomalies in the CMB might be evidence of contact with other bubble universes. Like if another universe came just close enough during inflation to nudge our own, it might leave a subtle fingerprint in the scale. One such anomaly is a cold spot, colder than it has any right to be. It spans a huge section of the southern sky, and it's been there in every satellite image, every survey. It could just be a statistical fluke, it could be a vast cosmic void, or it could be a scar. Left behind by a cosmic collision we'll never be able to replay. Of course, this is still speculative, debated, unconfirmed. But let's be honest, so is everything at this altitude. Even if we never detect other universes, the CMB still gives us something extraordinary. A limit, not a border, not a wall, but a cosmic curtain. Beyond it lies the time before transparency, before light, before anything could leave a mark. You drift closer now, not to the CMB itself, you're already in it, but to the concept of it. The understanding that you live inside a time capsule, and that the outer shell of your observable universe is this gentle hum. No matter where you point your sensors, you hit it, like the inside of a sphere softly glowing in every direction. And here's the mind-bending bit. Because space has expanded since that light was emitted, the region of space where that radiation originated is now about 46 billion light-years away in all directions. Which means you're floating in the centre of your observable sphere, not because you're special, just because every observer is. It also means that if you could see farther, if the CMB weren't there whispering this far, no farther, you might glimpse something beyond. More space, more galaxies, more structure, or maybe nothing. That's the mystery. The CMB is both a gift and a veil. It tells us how space evolved. But it also marks the horizon of visibility. Beyond it, darkness, not because it's empty, but because it's still forever, unreachable. You float there now, just outside the curtain. It stretches around you like a sphere of ghostlight. Beyond it lies time itself, still hiding in opaque plasma. And beyond that, we don't know. We probably never will, but here's a cozy thought before you sleep. The CMB isn't just ancient, it's still here. Every second it's bathing you, moving through you, a sea of primordial photons that touch every inch of space all the time. You're wrapped in the universe's memory. It's cold, about 2.7 Kelvin to be exact, but not lifeless. It's the sound of space continuing, quietly, softly, always. And if space ever does end, then it might be this echo that reaches the boundary first, a gentle knock. A final note, or maybe it just fades. Not because there's an edge, but because there's no one left to hear the hum. The light behind you has dimmed. The glow of the cosmic microwave background fades into the infinite hush, and now you drift through something stranger. Not silence exactly, but a kind of invisible urgency. You can't see it. You can't touch it, but it's pulling, stretching, accelerating everything around you like a silent conductor waving an invisible baton. Welcome to the reign of dark energy, the great expansionist, the cosmic landlord you've never met, but who's raising the rent on space itself? You look around, expecting fireworks or maybe a glowing nebula with a name like Zone of Expansion, but there's nothing, just more of everything drifting away from everything else, like shy partygoers trying not to make eye contact. Except it's not shyness, it's acceleration, and it's getting faster. This is not what we expected, by the way. For most of the 20th century, scientists assumed the universe's expansion caused by the Big Bang would eventually slow down, maybe even reverse. You throw something upward, gravity pulls it back. Basic physics, right? But in the late 90s, two teams studying distant supernovae discovered something no one saw coming. The universe's expansion isn't slowing down, it's speeding up. Historians still argue whether this was the most significant cosmological discovery since Hubble's redshift observations, but the data was clear. These distant exploding stars weren't just far, they were too far, as if the space between them and us had stretched more than it should have. Something was pushing space apart faster and faster, and that something was dubbed dark energy. Not because it's spooky, though it kind of is, but because we have no idea what it is. It's not a force, it's not a particle. It doesn't clump, it doesn't glow, it just is. A constant energy woven into the fabric of empty space. And the more space you have, the more dark energy you get, because it doesn't dilute as space expands, it stays constant. Which means the more space expands, the more dark energy there is to drive more expansion. It's a feedback loop, and it's turning the universe into a giant game of cosmic keep-away. Picture galaxies as raisins in a rising loaf of bread. Except the dough doesn't just rise, it accelerates. Raisins fly apart, clusters unravel. In time, only the closest raisins will remain in view. You, dear listener, are one of those raisins. You float now between galaxy clusters that once huddled together, bound by gravity. But the bonds are weakening. Not because gravity is tired, but because dark energy is just that good at what it does. Pulling space outward, not with force, but with the quiet confidence of an unstoppable idea. Right now, dark energy makes up about 6% of the total energy in the universe. That's most of everything. Dark matter, the runner-up, gets about 20%. Ordinary matter, the stuff you, I, stars, tacos, and Shakespeare are made of? Just fun. Yeah, you're the garnish on the cosmic salad. And while dark matter pulls things together, dark energy is tearing them apart, slowly, inevitably. Not with violence, but with apathy. So what does this mean for the question? Does space end? Well, if space is expanding faster and faster, and the rate of expansion keeps increasing, then over enough time, every part of space becomes unreachable from every other part. This isn't just about observation, it's about causity, about what can interact, about what can matter. Eventually, dark energy will stretch space so much that only our local galaxy group will remain visible. All the other galaxies, gone, not destroyed, just over the horizon, their light redshifted into oblivion. Their story's untellable. It gets worse. If dark energy becomes even more dominant, if its strength increases over time instead of staying constant, then we face something cosmologists call the Big Rip. Sounds dramatic, and it is. In the Big Rip scenario, the expansion of space eventually overcomes everything. First, it pulls apart galaxy clusters, then individual galaxies, then solar system, planets, eventually atoms. Even the strong nuclear force, the thing that holds atomic nuclei together, gets overpowered. Everything stretches until there's nothing left to stretch. Quirky side note, in this model, the Big Rip happens on a specific timetable. Galaxies unbind billions of years before the end, solar systems a bit later, planets shortly after, and atoms, they get maybe 10-19 seconds of warning. Just enough time to go, oh no, before dissolving into stretched out nonsense. Will the Big Rip actually happen? Most physicists don't think so. The best current data suggests that dark energy is a cosmological constant, meaning it stays the same over time. No increase, no Big Rip. Just steady acceleration until we're all alone in the void, waving politely at the darkness. But that still means the concept of space ending becomes meaningless, and if every part of space is speeding away from every other part, then there's no centre, no edge, no rest frame, just isolated islands shrinking not in size but in relevance. You drift now through one of those islands, the stars are the same, the physics the same, but the sky is emptier, quieter. The cosmic background radiation has redshifted into silence, the galaxies are gone, and you are left with only your neighbourhood, your cluster, your tiny cosmic cul-de-sac. It's peaceful, but final. Dark energy doesn't stop you from moving, it just makes the destination vanish, so maybe space doesn't end, but it erases itself from your reach. Think of it like walking down a hallway that extends forever, but the floor behind you is crumbling and the walls ahead are moving faster than you can run. You can still walk, you just can't get anywhere. And over time, the hallway gets quieter, the lights dim, not because they turned off, because the light can no longer catch up to you. This is the fate dark energy offers. Not death, not collapse, just separation, forever. A universe divided not by barriers but by velocity. Still, there's something oddly soothing about it, isn't there? You float, you watch the light fade, you accept the expansion, and space, always polite, never says goodbye, it just grows. You're barely moving now, not because there's friction, space is too polite for that, but because there's simply nowhere urgent to go. Everything is drifting. Galaxies recede into darkness. Light stretches into silence. Even time feels drowsy, like it's curled up on itself and taken a long nap across your lap. And in this stillness, another thought rises. Not where does space end, but when. You've been thinking of space as distance, direction, geometry, expansion. But what if space has more in common with time than with width or height? What if the edge of space isn't just out there, but ahead of you? Tonight we're turning toward a concept that's not just cosmic, it's personal, time as a dimension. Let's back up, way up. In Einstein's relativity, time and space are part of the same four-dimensional fabric, space-time. You can't move through space without affecting your movement through time, and vice versa. Time isn't just a ticking clock, it's a coordinate, like a cosmic zip code that keeps changing as you move. That means space and time aren't separate, they're woven together. When the universe expands, it's not just stretching out space, it's stretching space-time. Time has shape, direction, structure. And if that's true, could time have an edge, just like the spatial kind we've been chasing? Could space end because time does? Historians still argue whether time was truly understood as a fourth dimension before Minkowski formalized it in 1908, building on Einstein's work. But once it was added to the math, our entire concept of the universe changed. Suddenly, we weren't just in time, we were part of it, carved into the block like a wrinkle in space-time itself. So here's the wild thought. If space is expanding and time is part of space, then isn't time expanding too? What would that even look like? You drift now not through space, but along time. It feels smooth, but slightly tilted, like you're walking down an endless escalator, not being pulled exactly, but nudged forward. You can't stop, you can't turn around, you just ride it. That's because time, unlike space, has a preferred direction. The arrow of time. Forward. Always forward. But what defines that direction? Mostly entropy, the tendency of systems to go from order to disorder, from a deck of cards arranged by suit to a mess of clubs, spades, and a joker stuck to someone's forehead. The universe started in a low entropy state, hot, dense, smooth, and since then it's been unraveling, cooling, mixing, becoming more chaotic. Entropy gives time its one-way street, And it might also give space its forwardness, because here's where it all loops back. If time is just another dimension, then maybe space doesn't need an edge. It could simply fade into time. Think of a cone, not the ice cream kind, though. Honestly, well earned by now? No. Picture a light cone. The past narrows behind you. The future fans out ahead. And you're right at the tip, always at the tip. The only place the present can exist. You float in that moment now, right between what has been and what might be, and ahead of you, a horizon, not of space, of time. Some theories, like those behind the Big Freeze, say the universe will keep expanding forever. Stars will die, black holes will evaporate, eventually all activity will cease, entropy will hit its maximum, and time will lose meaning. No events, no change, no clocks. That's a kind of ending, isn't it? Not a wall, not a border, but a thermodynamic fade-out. In that final universe, nothing happens, not because it's too cold or too empty, but because it's too still. No difference from one moment to the next. No arrow of time, just sameness. Imagine standing in a hallway where every step forward looks identical to the last. At some point, forward stops mattering. That's how time might end. And if time ends, what happens to space? Well, if space is bound up with time, then space too could reach a point of stillness. Not ended, like a dropped storyline either, but a paused, like a TV show frozen on the last frame, forever. Other models suggest more dramatic outcomes. The Big Crunch, where gravity reverses expansion and pulls the universe back into a final singularity. In that case, time could collapse, contracting like a rubber band snapping back. Space wouldn't end at a wall, it would end at a point. A final convergence of every particle, every moment, every possibility. Or take the Big Bounce idea. In this one, the universe collapses and then starts again. Not as a reset, but as a continuation. Maybe time reverses, maybe it loops, maybe your next existence is already in motion, behind the scenes like a sequel in pre-production. Here's your quirky tidbit. In some speculative models, time is just a property of the universe's quantum state, an emergent phenomenon. That means if the universe stops changing, time itself disappears. Like a mirage, it never was a thing, just a side effect of change. So when we ask, does space end? We have to ask, does time end? Because they may not be separable at all. And here's a quiet, slightly haunting idea. If time ends, we won't know it. Not because we'll be gone, but because the very concept of knowing requires time. You'd be frozen in the last thought. The last tick of the cosmic clock, held there, timeless, perfect, unchanging, kind of like now, because at this point in our journey, you're not really floating anymore. You're suspended, weightless, not just in space, but in thought. And so we slow, not because we've found the end, but because the question has expanded beyond geometry and galaxies. Now, it lives in rhythm, in change, in when, because a status might not end where you can't go. It might end where there's no longer anywhere or any when left to go. And now, dear listener, it's time to rest. Listen, wind down begins. Let your breath slow, let your thoughts uncurl. The stars can wait. The universe isn't racing toward a wall or slipping off an edge, it's drifting, expanding, breathing in long, soft cycles that stretch across eons. You're part of that rhythm, no need to chase it. No need to understand every curve or crack in space-time. The answers are out there, sure, but so is sleep. And tonight, sleep is the better journey. Maybe space does end, or maybe it folds, maybe it fades into time or into itself, or into something we can't name. And maybe that's exactly how it should be. Let the last starlight wash over you. Let the dark embrace you gently. You're floating in the middle of something beautiful, something vast, not at the edge, not at the beginning, just here, still. The stars are gone now. Not gone, just quiet. You're not surrounded by galaxies anymore. You're surrounded by questions, heavy ones, the kind that hover just outside of logic, the kind that tilt your perspective in ways you weren't quite prepared for. Because if all this, the stretching space, the untraceable horizon, the fading light, feels too carefully constructed, too elegant, too convenient, then maybe it is. Maybe space doesn't end at a wall, a fold, or a fade. Maybe it ends at the edge of the simulation. Yes, we're going there. Let's peel back the last layer of cozy cosmic comfort and ask, what if this isn't real? Not in the your dreams are illusions kind of way, but in the literal, high-resolution GPU-burning sense. What if space doesn't go on forever? Because it only renders what you look at. Welcome to the simulation hypothesis, where physics is just code, atoms are pixels, and space ends, not at a boundary, but at the edge of a rendering engine. Let's take it from the top. The idea is simple. If technology continues to evolve, and if civilizations become capable of running highly sophisticated simulations, then statistically, mathematically, it's likely that we are not the first beings to ever reach that level. And if that's true, then it's also likely that some of those civilizations might simulate entire universes. You are now, quite possibly, a highly detailed NPC. This thought experiment was formalized by philosopher Nick Bostrom in the early 2000s. He suggested that one of three things must be true. 1. Civilizations never survive long enough to simulate universes. 2. Civilizations survive but never choose to simulate universes. 3. Civilizations simulate universes, and we are probably living in one. Option 3 is the disturbing one, and also weirdly the most likely if you trust probability more than intuition. Now, if we are in a simulation, then the rules of physics might not be laws, they might be constraints, programming choices, parameters set by the cosmic dev team to keep things interesting but stable, like gravity on medium difficulty. And space? Space becomes less of a cosmic frontier, and more of a rendered environment. You don't simulate the entire universe at once. That would be wildly inefficient. You simulate what's needed, what's being observed, like a video game world that loads the terrain around your character, but keeps the rest as low-res background. Think of Minecraft, or No Man's Sky, or literally any open-world game. When you walk forward, the game renders what's ahead of you. Walk backward, and it renders that instead. What's out there isn't fully loaded until you go there. Now scale that up. Way up. What if the speed of light isn't a fundamental constant? It's a bandwidth limit. What if quantum uncertainty isn't randomness? It's lazy rendering. And what if the edge of space is simply where the simulation stops loading? Quirky side note, some physicists have seriously proposed experiments to test whether space is discrete, like pixels in a simulation. One suggestion involves measuring the energy of cosmic rays at extremely high resolution, looking for grid-like patterns that might indicate a hidden simulation lattice. So far, no luck. But the idea is out there, blinking slowly in the shadows of the mainstream science. Historians still argue whether Plato was, in his own way, an early simulation theorist. His famous allegory of the cave describes people who live chained in a cave, seeing only shadows on a wall, mistaking those shadows for reality. They don't know the truth until one escapes and sees the outside world. That sounds awfully like an unplugging scene, doesn't it? But let's say it's true. Let's say you're in a simulation. That doesn't necessarily mean the universe ends, but it might mean space is conditional. It exists as long as it's being calculated, simulated, experienced. So if you travelled far enough for long enough in some direction, what would happen? Option 1, the simulation expands with you, rendering new space as you go. Endless generation, like cosmic Minecraft in creative mode. Option 2, you reach a rendering limit. Space fades, stars become placeholder code. Eventually you hit the edge, not of space, but of attention. The simulation never expected you to come this far, there's nothing left to load. Option 3, you get looped, like a loading screen background. Space just recycles itself. You think you're moving forward, but you're walking through the same copied patch over and over. Very efficient, very eerie. And then there's option 4, you break something. Maybe the simulation can't handle your trajectory, maybe your velocity, your position, your curiosity pushes too hard, and space begins to glitch. Not violently, just subtly. Stars duplicate, distances distort, the redshift doesn't behave, you see yourself ahead of you and behind. The background radiation hums at the wrong frequency, and then nothing. A full stop, not a wall, not a crunch, just no more data. Is that the end of space? Or just the end of what was meant to be seen? In a simulated universe, even asking if space ends is a risk. It's like shaking the snow globe too hard and expecting it not to notice. You've started digging into the engine room of reality. And the devs? They might not like questions. But here's the comforting part. Even if it is a simulation, so what? It's still beautiful. still full of galaxies and dark energy and paradoxes and pineapple on pizza, a true glitch depending on who you ask. The experience is real. Your reactions are real. Your dreams are real, even if the walls around them are procedural. Maybe space ends, maybe it doesn't. Maybe it's all just a clever trick of resolution, but if you turn around and head back toward the stars, you'll find they still burn, still orbit, still whisper, whether they're made of atoms or algorithms. You look forward again toward that last patch of unrendered black, and you wonder, what's waiting just beyond the edge of calculation? The darkness ahead feels different now, not the usual cozy infinity of deep space, but something denser, heavier, a pull, subtle but relentless. Like gravity got tired of being polite and started whispering your name. You drift toward it, not by choice exactly, but by surrender. The light around you starts to bend. Stars distort into stretched smears. Shapes spiral. Time slows. Not metaphorically, but literally. Because now you're approaching the most extreme structure space can offer. A black hole. You don't fall. You slide. You're drawn ever so gently into a trapdoor in the fabric of space-time. This is where space doesn't end, but it folds, curves, collapses. And here's the real kicker. This isn't even rare. There are likely hundreds of millions of black holes in our galaxy alone. Quiet ones, busy ones, hungry ones. Some the size of cities, some the size of entire solar systems. And at the center of nearly every galaxy, including ours, there's a supermassive black hole, weighing millions or even billions of times more than our sun. So what are they? In the simplest terms, black holes are regions of space where gravity is so intense that nothing, not even light, can escape. The edge of a black hole is called the event horizon, and it's not a solid surface, it's a boundary, a point of no return. Cross it and you're toast. Very slow motion, very distorted, very spaghetti-shaped toast. Historians still argue whether John Michel, an 18th century English clergyman, deserves credit for first imagining something like a black hole. He called it a dark star puissant, which sounds metal, but the math didn't catch up until Einstein. And even then, Einstein himself didn't quite believe black holes could really exist. Too extreme, too singular, too inconvenient. Turns out the universe doesn't care if you find it inconvenient. You are now nearing a black hole's event horizon. And from your perspective, something strange happens. As you approach the horizon, you slow down, but only to an outside observer. To you, everything seems normal, until it doesn't. Because space and time begin to trade places. In normal space, you can move forward and backward in space, but only forward in time. But inside a black hole, time becomes a direction that leads inward, and space becomes the dimension you can't escape. You're not falling toward the center. You're moving forward in time toward a future that just happens to include being crushed into infinite density. You can't back out. The script has already been written. That crushing center is the singularity, the theoretical point where space-time curvature becomes infinite, where the known laws of physics break down entirely, not because they're bad laws, but because they never expected to be working under these conditions. It's like asking a toaster to explain string theory. Good effort, wrong equipment, but here's where things get deeply weird and very relevant to our big sleepy question. Could space end inside a black hole? Well, yes and no, or maybe yes and yes, because inside that singularity, the coordinates that describe space become undefined. There's no more direction, no more movement. No left or right or farther, only in. Space has nowhere left to go. Time has nowhere left to tick. You reach a state where geometry itself breaks, where distances are meaningless and every path leads to the same impossible point. So in one sense, yes, space ends here. Not with a wall, with a collapse, a point so dense and so extreme that space simply folds into a mathematical riddle. But there's another possibility, one that's been teased, debated and whispered about in theoretical physics for decades. What if black holes don't end space? What if they lead to more of it? Welcome to the White Rabbit Zone, wormholes, Einstein-Rosen bridges and white holes. According to some solutions to Einstein's equations, a black hole could theoretically connect to another region of space-time. You fall into one mouth and emerge somewhere else, another place, another time, maybe another universe entirely. It's the ultimate cosmic shortcut. Fold the universe like a piece of paper and poke a hole through. Boom! Interstellar travel, no warp drive required. Of course there's a catch: wormholes are unstable. They collapse before anything can pass through, unless you have some exotic matter to hold them open. Spoiler, we don't. And even if one did stay open, you'd still have to survive the trip through regions of space-time that would stretch and crush you in beautifully cinematic ways. Still, the math says it's possible. Not proven, not practical, but possible. Quirky tidbit. Some physicists speculate that the inside of a black hole might be a new universe, that every black hole singularity could birth its own baby cosmos on the other side, a kind of cosmic recycling. In this model, our own universe could have emerged from a black hole in another universe. A universal Matryoshka doll. Space within space. Let that one float for a second. You sitting in your galaxy, orbiting your star, sipping your sleepy tea, could be inside someone else's black hole. So in this view, space doesn't end at the singularity. It transitions, it flips, it bounces, it sprouts new dimensions. Or maybe it does end, just for you. Not because the universe stops, but because you do. You cross the event horizon. You pass the point of no return. You reach the end of your space-time thread. But the universe, it keeps stitching. You float now just outside the event horizon, not falling in, just watching. The light bends around you in impossible curves. The stars twist into ribbons. The background radiation gets caught in a spiral it'll never escape. And beyond the veil, maybe an end, maybe a rebirth, maybe a space so twisted we don't even have words for it. So does space end here? If you stop at the singularity, yes. If the universe continues beyond it, no. If black holes are gateways to other places, then space is just redirecting traffic. But one thing is certain. Black holes don't care about your definitions. They bend every rule, break every map. And yet, they exist. Calmly, elegantly, universally. They are not monsters, they are boundaries. Not of space, but of meaning. And sometimes when space hits its limit, it folds and waits. You're drifting now through the deepest quiet. Not the comfortable stillness of open space or the disorienting hush of black hole gravity, but something different, something tense. Like the universe is holding its breath, waiting. Because this is where it all comes back around, where the expansion you felt, the stretching you followed, the light that's faded and the space that's grown, all of it might not go on forever. It might reverse. Tonight, you spiral gently through one of the oldest, most haunting cosmological questions. Will the universe collapse? And if it does, is that the end of space? Or just the beginning again? This is the land of the big crunch, the big bounce, and a few other cheerful theories that suggest our universe might not expand forever, but instead could someday fall inward, shrinking, heating, and possibly restarting in an endless cosmic cycle. Let's rewind. Again, we know space is expanding. We've seen it in red-shifted galaxies, measured it through supernovae, confirmed it with the microwave background. But for decades, scientists weren't sure whether this expansion was permanent or temporary. They imagined the universe like a ball thrown into the air. Gravity would decide what happens next. If there's too little matter, the universe expands forever, like a ball escaping Earth's gravity. If there's just the right amount, it slows down but never quite stops, like a perfect trajectory. If there's too much, gravity wins, the expansion halts, and space begins to collapse inward. That's the big crunch. Imagine that. A universe that doesn't end with a whimper, but with a gravitational scream. Galaxies collapsing, clusters crashing, space unfolding in reverse. The temperature rises, distances shrink, time begins to contract. Eventually all matter collapses back into a singular point, hotter than the Big Bang but in reverse. And what then? Some say that's it, the end. No after-party, but others propose something wilder, something cyclical, the big bounce. In this theory, the universe doesn't stop at the singularity, it rebounds. Space contracts until it hits some quantum floor, some minimum size, and then, bang, expansion begins anew. A new universe, a new timeline, a new roll of the cosmic dice. This isn't just wishful thinking, it's built into certain models of quantum gravity and loop cosmology. They suggest that space-time has a kind of quantized structure, like pixels, and can't shrink past a certain scale. Instead, it bounces, a little like compressing a spring until it rebounds. Quirky fact for your pillow tonight. In one version of the bounce model, The universe goes through endless cycles: bang, expand, stretch, collapse, crunch, bounce, repeat. Each cycle might last trillions of years, and each one wipes the slate clean. You might be living in cycle number 849,763 for all we know. Historians still argue whether ancient cyclic cosmologies, like those in Hinduism or Mayan mythologies, were genuinely conceptualizing a universe like this, or if they were describing cultural cycles metaphorically. But the idea that time and space might repeat is, in some ways, as old as storytelling itself. So how would this even work? You drift now through a cooling universe. Stars are dying, expansion has slowed, gravity begins to pull back, clusters move closer, then galaxies, then stars. You're not just watching space shrink, you're feeling time stretch in reverse. The arrow of entropy bends backward. Order increases, heat returns. You see the sky brighten, not with stars, but with compression, with fire. And then, in the final moment, everything is one. Not metaphorically, literally. One point, no space, no time, no before, no after. And then, a bounce, a bloom, a new beginning, or maybe not. Maybe the bounce fails, maybe entropy wins. That leads us to another apocalyptic daydream, the heat death. In this scenario, the universe doesn't collapse. It simply coasts toward emptiness. Expansion never stops. Galaxies drift so far apart they never meet again. Stars burn out. Black holes evaporate. Matter decays. And what's left is nothing. Not nothing in the poetic sense, just a uniform spread of low-energy particles. No change, no temperature difference, no usable energy, no events. Space still exists, time still exists. But nothing happens, a final eternal coma. So in that ending, space doesn't collapse, it doesn't fold, it just wears out. Like a song played too many times until there's only static. Still, even that might not be final, because space is sneaky, and time even sneakier. Some theories propose that in this final frozen state, quantum fluctuations could create something new. A bubble, a new universe, a restart, another Big Bang, born not of fire, but of boredom. You float now at the edge of one such possibility. The universe has shrunk or expanded so much that it's nearly featureless. You're a ghost in a waiting room, and suddenly the floor creaks. A fluctuation, a crack, a spark, not for you, not for this world, but for the next. Does that mean space ends, or that it renews? Maybe the edge of one universe is the womb of another. Maybe our Big Bang was someone else's big crunch. Maybe space, like you, needs to sleep before it wakes again. And maybe there is no final edge, just a rhythm, a cosmic inhale and exhale, a bloom, a fold, a breath, a bounce, and so you float here now, not at the end, but at a transition. A quiet between universes, a pause before possibility. Does space end? Maybe, but only to begin again. Space stretches, space folds, space collapses, space bounces, and just when you think you've mapped all its quirks, it pulls one last trick. It hides. Not in the shadows, not in the background radiation, not in the gaps between galaxies. It hides in directions you can't reach. Because tonight, you're not just floating through the familiar dimensions of up, down, left, right, forward and back. You're drifting toward the idea that space might continue, not outward, but sideways, into dimensions you've never seen. Welcome to the warped realm of extra dimensions. Let's begin gently. You live in a 3D world, right? You can move in 3 spatial directions and 1 temporal one, forward in time. That's it. But what if there are more spatial dimensions tucked behind the ones you know? Dimensions that aren't large like ours, but curled up so tightly you'll never notice them. This is a core idea in string theory, a candidate for the elusive theory of everything. According to string theory, the fundamental particles we observe, quarks, electrons, neutrinos, aren't points, but tiny vibrating strings. And those strings need more room to wiggle than our familiar 3D space allows. How much room? Up to 10 or 11 dimensions, depending on the version of the theory. The extra dimensions are compactified, rolled up like sleeping bags so small they make atoms look like cruise ships. They're hidden in plain sight, affecting particle behavior, gravity, maybe even consciousness, while staying frustratingly out of reach. And here's where it warps your sleepy little brain. If space ends in the directions you know, maybe it just turns in a direction you don't. Like a hallway that doesn't stop at the wall, it just curves off into an unseen dimension. You hit what feels like an edge, but it's not a barrier. It's a pivot. Space doesn't end. It escapes into dimensions you can't follow. Historians still argue whether early 20th century mathematicians like Theodor Kaluza and Oskar Klein truly understood the depth of their own ideas when they tried to unify gravity and electromagnetism using an extra spatial dimension. Their theory was beautiful, elegant, and utterly overlooked for decades, until string theorists dusted it off and said, "Wait, hold on," and then the floodgates opened. In string theory, these extra dimensions help determine what kind of universe you get. The way they're curled up, their shape, their topology, their vibrational modes controls the properties of particles, the strengths of forces, the constants of nature, different shapes, different universes. It's like cosmic origami. Fold the dimensions one way and you get our reality. Fold them another and you get something completely different. No gravity, no light, no socks. A true nightmare. Quirky tidbit: odd versions of string theory predict brain worlds. Our universe could be a three-dimensional brain floating in a higher dimensional bulk. Other brains might exist nearby in those extra dimensions, totally invisible to us but as real as our own. Yes, this is the same kind of brain we mentioned in multiverse theories. It shows up a lot. Apparently, the universe loves pancakes. You might be asking, if these extra dimensions are real, why don't we feel them? Well, imagine living on a sheet of paper. You can move forward and back, left and right, but not up. The idea of up is nonsense to you. It's not just unreachable, it's unthinkable. Now imagine something existing just above your sheet. Close, constant, but forever unreachable. That's what extra dimensions are to us. Not invisible, just orthogonal to our reality. And this brings us right back to the central question. Does space end? In a three-dimensional sense, maybe. But what if space continues into these hidden dimensions? What if the observable universe is just a slice? A projection of something larger? Like the shadow of a 4D object on a 3D wall? You float now at the edge of your known directions. You can't move forward. There's nothing more to see, but you feel it. The tug. The sideways pull of something beyond left and right. Not up, not down, something else. You reach out and your hand doesn't pass through a wall. It twists, folds, vanishes. Not into darkness, but into dimensionality you weren't built to comprehend. Let's turn to an odd thought experiment to help anchor this. Imagine a two-dimensional creature living on a piece of paper. It sees everything in its plane, then you, a three-dimensional being, touch the paper with your finger. The 2D creature sees only a circle. It has no concept of your finger's height, your hand, your arm. To it, you're just a strange event, a ripple in its fabric. Now flip that. What if what we perceive as unexplained events, quantum fluctuations, gravity anomalies, maybe even black holes, are intersections with higher dimensional objects? What if the universe is being touched from above? Suddenly, space doesn't need to end. It can just bend into invisibility, slide off into a hallway we don't have the keys to. Even more provocatively, some scientists believe gravity might be weak because it leaks into extra dimensions. That's right, gravity could be diluted across multiple dimensions, which is why it's so much weaker than, say, electromagnetism. You try lifting a chair, it's hard, electrons repel each other, and light particles race around with ease. But gravity? It barely holds things together unless you're talking planets. Maybe that's because part of it is missing. Maybe some of gravity is pulling toward a direction you'll never feel. Not outward, not downward, just elsewise. So what does this mean for the end of space? It means our idea of end is a limitation of perception. It assumes all directions are knowable. It assumes all space is ours. But if space continues into higher dimensions, then what we think of as a boundary could be more like a dimensional cliff. You don't fall off. You just fall through. And maybe, just maybe, what feels like the end is actually a new direction waiting for someone, or something, to figure out how to walk it. So float here a little longer. Feel the air around you bend, not in your usual three ways, but in whispers and twists your body can't follow. Something's there, not here but not gone, and space, it never ends. It just turns away. You've drifted through folds, loops, boundaries, and bounces. You've followed space to its conceptual edges, stared into its collapsing centers, even peeked down its hidden dimensions. But now, here it gets especially strange. Because tonight, you're not just asking how space might end, you're asking what it would mean to be outside of it. If there's an edge, after all, some kind of border or boundary, then what's beyond it? What does it mean to be outside the map? When the map includes everything, you float now in that philosophical limbo, the borderless lands of existence, not beyond galaxies, not beyond time, not even beyond physics, beyond space itself. Let's start by admitting something humbling. The human brain was never designed for this. It evolved to throw rocks, build shelters, and awkwardly explain memes. It didn't evolve to grasp what outside the universe means, because as far as your wiring is concerned, outside implies another location, something next to, behind, or surrounding the thing you're inside of. But space isn't in something. Space is the arena. It is the container. So the concept of an outside to space doesn't really work. Unless you're ready to rethink the very nature of containers, let's take a breath. We're going to need it. In physics, our universe is often modelled as a manifold, a kind of mathematical space that can be curved, stretched, connected, and shaped. The key is that you don't need an outside to define it. Just like you can walk endlessly on the surface of a sphere without ever needing a beyond, the universe can be complete, self-contained, and yet entirely without an external frame. This is sometimes described as closed but unbounded, finite in volume, but with no edges, no cliffs, no outside. Historians still argue whether the ancient notion of the celestial sphere, used by Greek, Indian, and Islamic astronomers alike, was intended as a literal boundary or just a convenient visual metaphor. But in either case, it was framed as something within a larger order. God, the prime mover, the divine heavens. Modern cosmology takes a very different view. The universe might be the only room that exists, and if space ends anywhere, it doesn't end into something else, it just doesn't continue. That's weird. But it's also strangely consistent. After all, what's north of the North Pole? Nothing, not because there's a wall, but because north stops making sense. In the same way, asking what's outside the universe might be like asking what's outside geometry, or what's beyond math. You're reaching beyond the frame, and there may not be anything there to reach into. Still, some theoretical models do flirt with the idea of an outside. In brain cosmology, for example, our universe is one 3D membrane in a higher dimensional bulk. In this view, the bulk is the outside of particular universes might bump into each other, collide, leak gravity, swap information. But can we get out into that bulk? Probably not. We're stitched to our brain, like ink drawn on paper, beautiful and stuck. Or maybe the outside isn't spatial at all. Maybe it's mathematical. In the mathematical universe hypothesis, our reality is just one of many possible mathematical structures, each as real as ours, even if completely inaccessible. So outside the universe doesn't mean a bigger room, it means a different equation, a universe with different constants, different symmetries, one where the value of pi is something horrifyingly rational, or time flows sideways and sentient triangles wonder if their space ends. You float now at the limit of model and metaphor. You're not facing a wall, you're facing a lack of coordinates. Because here's the quiet truth. Space doesn't need to end into anything. It can simply be all that is. It's like being a character in a novel asking what's outside the story. There is something, the author, the paper, the reader, but from inside the story, it's unknowable. Maybe the same is true for us. Quirky tidbit. Some models of space-time suggest that the universe is a hologram, a projection of information from a lower dimensional surface. In this case, the real universe might be a kind of mathematical boundary, and everything we experience as 3D is just an emergent illusion. Space wouldn't end, it never began. So where does that leave us? At the edge, perhaps. Not a physical place, not a glowing line in the sky, but a conceptual boundary. A place where our tools, language, math, imagination begin to fray. You're here now, floating at that fringe, beyond which there may be nothing. Not emptiness, not void, just no space at all. And what does that feel like? It feels like you. Thinking about it. Filling the silence with wonder, because maybe outside the universe isn't a please. Maybe it's a question, one that exists not in space but in you, in your brain, in your language, in the capacity to ask what lies beyond the possible. Maybe space ends at the point where curiosity hits its ceiling, and maybe that's the most beautiful boundary of all. So you rest here, not outside, not inside, just aware, balanced on the edge of the knowable. No walls, no next room, just the sense that you've reached the farthest thing there is, a thought that can't go farther. You're still here, still weightless, still drifting at that dizzying edge where the universe seems to blur, not into void, but into meaning. The stars behind you have faded, the questions ahead have no shape, and now we circle back to something a little closer to the ground, closer to the heart. Because there's one piece of this puzzle that's been quietly orbiting everything we've explored so far. Why do you want space to end at all? Tonight you're not floating through wormholes or dimensions, you're floating through your own expectations. Because behind the science and the equations and the beautiful brain-melting models, there's a very human story. We like endings. Not there because we're morbid, but because we're wired for narrative. Every story you've ever loved had a beginning, a middle, and an end. The arc, the resolution, the payoff, the what happens next. Even bedtime stories, especially bedtime stories, wrap things up neatly. Once upon a time, and they lived happily ever after. But space refuses. It stretches beyond what we can see. It might loop, it might stretch, it might split, fold, bounce, or simply converse or continue. But it doesn't give us a tidy final chapter, and that's deeply unsatisfying. Because when we ask, does space end, what we often mean is, can I know the shape of the story I'm in? Is there closure? Will I reach the edge, the answer, the aha moment that tells me what this all means? Historians still argue whether humanity's oldest cosmologies were attempts to explain the world or to comfort ourselves. The Babylonian dome, the Egyptian sky goddess Nut, the Norse world tree Yggdrasil. These weren't just scientific guesses. They were stories, enclosed, complete. The universe had an edge, a top, a bottom, a purpose, and we loved it that way. Even today, when we stare into the observable universe, we still speak of edges. The edge of the visible universe, the end of time, the boundary of the known. As if space is a video game map, as if the final zone is just waiting to be unlocked. But what if that instinct, so deep, so familiar, isn't describing the cosmos at all? What if it's describing us? You, floating now in infinite night, are still a human. And humans are end-seeking creatures. You like plots, you like structure, you like knowing there's a final season, even if it's disappointing, looking at you lost. When you ask if space ends, you're also asking if you have a place in it, if the universe has a frame, if your life is part of something finite enough to hold meaning. But the universe doesn't seem interested in delivering that kind of comfort. It gives you infinite loops and unobservable regions. It gives you bubbles, brains, and endless inflation. It gives you eternal expansion and dying stars and information paradoxes. It gives you a canvas too large to frame and no gallery to hang it in. Quirky side note, in storytelling there's something called the closed world assumption. It means that if something isn't stated explicitly in the narrative, it doesn't exist in the story's world. Fantasy novels love this, so do puzzle games. The player assumes the world is complete and bounded. Cosmology is the opposite. The more we discover, the more we realize how little of the universe is even reachable, let alone readable. We live in an open world reality, with no final chapter, no confirmed map, no boss level, just more. So you might be wondering now, does that make everything feel pointless? Strangely no, because meaning doesn't have to come from a defined edge. It can come from the path, from the wandering, from the asking. And maybe that's where space and story diverge. A story ends, space just continues. And in that gap between structure and freedom, there's something surprisingly tender. The permission to let go of needing an ending. Not everything has to be closed to be beautiful. Not every question has to be answered to be valuable. Not every edge has to be sharp to be real. You float now not toward a wall, but toward a new way of thinking. That the end of space might not be a location. It might be a boundary of imagination. And your imagination? It doesn't end either. Because space doesn't care about narratives. It's not telling a story, it's you are. You're the one building arcs and patterns out of stars and background radiation. You're the one tracing meaning across distances that will never respond. You're the one asking questions that no telescope can answer. And that's okay. That's enough. Let the universe be messy, open, unfinished. Let it stretch past your gaze, past your math, past your capacity to dream it all at once. Let it be too big, too fast, too quiet. Because in that bigness you find humility, and in that humility you find awe. So no, space doesn't end the way you want it to. It doesn't wrap up cleanly, it doesn't write a final scene, it doesn't care if your story has a climax or closure, but you do, and so you write them anyway, in bedtime questions, in telescopic dreams, in starlit whispers. Does space end? Maybe not. But the question? It's a very good place to pause. You're nowhere now, no up, no down, no distant galaxies twinkling like reminders, no cosmic background, whisper humming in your ears, just you, drifting in a space that's no longer space, wrapped in a silence so deep it almost feels like it's listening back, and yet something remains, a presence, a you-ness, still wondering. Does space end? You've asked the question in every language you have, in physics, in geometry, in metaphor, in myth. You've traced its borders through expanding galaxies, sneaky loops, ancient light, bubble universes, dying stars, and higher dimensions so tightly curled that they might as well be whispers. You've followed the thread to where gravity tears geometry apart. You've looked beneath the simulation's rendering layer. You've hovered beside black hole horizons, drifted across time's collapsing arrow, and even stared beyond the veil of knowability itself. And yet, here you are, not at an edge, not at a wall, but in the middle of something that may not have a middle at all. Because the truth might be this: there is no edge of space, no outscene, no final corner to tuck under. Space might be finite, or infinite, or finite but unbounded. It might be part of a multiverse, a brain, a loop, a bounce, or a glitch. It might continue forever in some directions and wrap gently in others. It might stretch until meaning itself grows thin. But end? That's a word for books, for episodes, for days. The universe isn't concerned with endings, and it's not even sure what a conclusion is. Quirky side note, some cosmologists have proposed that even if the universe is infinite, the information you can access is finite. This would mean that you and everyone else live in a kind of causal prison. The observable bubble we talked about all the way back in section 3, that's your forever home, not because of walls, but because of light cones, those sneaky diagrams that define the limits of what you can affect and perceive. In other words, you don't hit the end of space, you hit the end of influence. You're not everywhere, you're here. And space stretches on, both beyond your reach and inside your mind. Historians still argue whether the first people to ask about the shape and end of the universe really wanted scientific answers, or just comfort. Maybe those ancient skywatchers weren't trying to measure distance. Maybe they were trying to measure meaning. Where do we fit? How far does this go? Is there a boundary where we stop being small? Because when you ask, does space end, what you're really doing is looking for orientation. You're building a map of home, and the stars, distant, cold, indifferent, are somehow part of that map. You float now, not just through theoretical physics, but through the soft breath of something very human. A need not to control the universe, but simply to understand where it ends and we begin. But maybe that's the twist. Maybe you are the center of something endless. Maybe consciousness is a fixed point in an unbounded story. Maybe meaning is local, but that doesn't make it small. Maybe space doesn't end, but curiosity does not need it to. You've asked the question, you've floated through the answers, and now you know what the edge of space really looks like. It's a mirror, and in it you see something extraordinary, not the cosmos, not the equations, not even the horizon. You see a small, soft, flickering mind brave enough to wonder. And maybe, just maybe, that's how space knows itself. Through you, through questions like this, through the quiet that follows when all the light has gone. You're not at the edge of space, you're inside the middle of mystery. Still floating, still awake, still asking. And space, it's not trying to escape you, it's letting you in. Everywhere, always.